Hello, and welcome back to the course on Physics for Engineers. We are still on Chapter 8, which is all about waves and oscillations. So before we proceed, let us first review some of the concepts that we have discussed in the previous lessons. So we have discussed about simple harmonic motion, where we define the angular frequency to be equal to the square root of the force constant over the mass, the oscillating mass. And if you have a damped oscillation, your angular frequency will actually be lessened due to this damping parameter or damping constant here, B. So for this lesson, we will be talking about resonance and wave interference. So let's first discuss what is a forced oscillation. So these are oscillations caused by an additional periodic driving force. So usually in real situations, the simple harmonic motion is actually an ideal situation. Any types of oscillation usually involves damping. So if you want to create a simple harmonic motion, you need to add a periodic driving force. So you need to force the object to oscillate into a simple harmonic motion. So that's actually what forced oscillation is about, an addition of periodic driving force. So forced oscillation can actually create resonance. So these are forced oscillations of an object wherein the driving force frequency or the periodic driving force frequency matches the natural angular frequency of the object. So objects can actually have a natural angular frequency. This is actually the frequency wherein the object starts to oscillate. So, of course, if the driving force frequency matches the natural angular frequency, then you force the object to oscillate, and that is what we call resonance. So here, it's an example of not a very good example of resonance, actually. So you have a bridge that is oscillating because there's an earthquake, and the frequency of the earthquake, so the earthquake is your driving force, matches the natural angular frequency of the bridge, causing the bridge to oscillate. So as an engineer, as a civil engineer, you really need to take into account or take into consideration the natural angular frequency of the bridge or the buildings that you are constructing, not as to so that they will not match any known frequencies of earthquakes. Another example of resonance is your radios. So basically, in radios, you are actually tuning. That's what happens now when you match the frequency of your radio to the frequency of the radio station, and to create resonance. So that's an example also of resonance. So another example of resonance is basically when the DJ forces you to oscillate, forces you to go with the beat or to go with the frequency that he plays. So that's also an example of resonance. So in our case, our bodies can actually resonate at different types of frequencies, angular frequencies. So basically, when the DJ plays a song, your body will resonate. So when your body starts to oscillate, that is what we call resonance. Okay. So another property of wave, when they meet or overlap, is they interfere. So there's wave interference. So there's constructive interference if the interfering waves are in phase. So when they are in phase, they usually produce a resulting wave or a resultant wave which has a much larger amplitude than the original waves. If the two waves undergoes destructive interference, then they are most probably out of phase, and they will produce a resulting wave or a resultant wave which has a very small or nearly zero amplitude. So this is an example of a simulation of wave interference. So we have wave 1 and wave 2. And whenever the two waves, wave 1 and wave 2, are in phase, such as this moment here, you will notice that the amplitude is greatest. But when the waves, wave 1 and 2, are out of phase, say wave 1 is a crest, wave 2 is a throw, then you will get a destructive interference. So this one, destructive interference, wave 1 is a crest, wave 2 is a throw. But when they are both crests, when they are in phase or in sync, they produce a larger wave. So that's constructive and destructive interference. So aside from interference, waves can also be reflected. And basically, wave reflection is just the bending back of a wave when it hits a boundary. So when a wave hits a boundary, it will be reflected, and actually it will interfere with itself, the original wave. And when that happens, when the incident wave interferes with the reflected wave, they can usually form standing waves. Not all of the time, but there's specific conditions that they can create standing waves. Waves that doesn't appear to be moving. So standing waves is a manifestation of resonance. So if you have produced standing waves, then there's actually resonance happening. So this is an example of an animation for standing waves. So you see green waves going to the right, and then the blue waves are actually the reflected waves. So the green waves moving to the right, they hit a boundary and they get reflected and they become the blue waves. So you will notice that they will undergo constructive and destructive interference. And the red wave that you see here are the resulting wave. The interference between the incident wave, the green wave, and the reflected wave, which is the blue wave. So if we try to remove the incident and the reflected wave and only focus on the resultant wave, this is what we see. You will see a wave that doesn't appear to be moving. Hence, it is called a standing wave. So it's not literally standing, but it's not moving, so it's called standing waves. So this wave doesn't appear to be moving to the left or to the right, so it must be standing. So that's a standing wave. So a standing wave has antinodes. These are points of constructive interference. So the points here, 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 and here. So in this simulation, you can actually see four antinodes, the points of constructive interference. And a standing wave also have nodes. These are the points of destructive interference. So these points here. So in this case, it has 5 nodes. So 4 antinodes and 5 nodes. So these are the points wherein the overlapping or interfering waves have 0 amplitude. The resulting wave is 0 amplitude. Okay. So let's consider standing waves on a string. And let's only consider the case where the string is fixed at both ends. So in this case, in order for standing waves to occur, or for resonance in the string to occur, there are only specific wavelengths allowed and specific frequencies allowed. So the allowed wavelengths are 2L over N, where L is the length of the string, and N is an integer from 1, 2, 3, and so on. And these are the corresponding frequencies. So from our formula, from the periodic wave equation, V is equal to lambda times F. So F is V over lambda. So lambda is 2L over N, so V over lambda. And you get the frequencies. So these frequencies are what we call the harmonics. So these are all the allowed frequencies for standing waves, in order for standing waves or resonance to occur on a vibrating string. So these are only the allowed frequencies. So F1 is what we call the first harmonic or the fundamental frequency. F2 is the second harmonic, and it's also called the first overtone. So F2 and above are called overtones. So F3 is the third harmonic, and it's also called the third overtone, and so on. So these are the what will the waves on a string, standing waves on a string look like? If it's vibrating at the fundamental frequency, then you will see a string vibrating in this manner. You will only see one loop produced by the string. So one antinode, two nodes. If the string is vibrating in F2 mode, then you will see two loops. You will see three nodes and two antinodes. So the number of antinodes correspond to the number of loops that you can see on the vibrating string. And then for F3, you see three antinodes or three loops. And for F4, if the string is vibrating on F4, then you will see four loops. Again, these are just the resonant or the standing wave frequencies of the string. If the frequencies of vibration doesn't match these frequencies, then you will not see these interference patterns on the string. So in a real scenario, your string will look like this. So you can actually do this in an actual scenario in the laboratory. So this is a string vibrating in F1. So in this case, the string is actually one half wavelength long. Here, the string is vibrating in F2 and it's two wavelengths long, one wavelength long. Here it's 1.5 wavelength long. Here it's two wavelengths long, or it's vibrating at F4. So that, or the fourth harmonic. So in the new normal of learning, since we don't have an actual laboratory, we will just use a simulation. And in the simulation, we can still find the frequency wherein the wave going to the right will be reflected back from this boundary, and they will interfere to create standing waves that doesn't appear to be moving to the left or to the right. So you can still imagine it using this simulation here for the laboratory to visualize this. So a string has what we call linear mass density, the ratio of its mass and its length. It's denoted by the variable mu. And the speed of a transverse wave on a string, V, is actually related to the tension and the linear mass density. So F here is the force or the tension in the string. So it's equal to square root of F over mu. So we can now write then our harmonics in a string as NV over 2L, or N where V is square root of F over mu over 2L. That one. So if you have a guitar string usually only vibrates in the fundamental frequency F1. So if we were gonna go back, the guitar string will just vibrate in this manner. Unless your guitar is very, very loose, then maybe you can see F2. So the tension in the guitar is usually adjusted so that it will only vibrate in the fundamental frequency. And the standing waves in the guitar string actually forces the air inside the guitar to oscillate, to resonate, and produce sound waves. Similar to how our vocal cords generate sound waves through our windpipe out of our mouths. So that one. So we are now relating here standing waves in the string and standing waves in inside the guitar. So the standing waves in the string are transverse waves, but the sound waves produced by the guitar are actually longitudinal waves. It's another type of wave. So we will actually discuss about standing sound waves and sound resonance in the next lessons. So let's have an example. So this is resonance in a guitar string. So when you strum a 0.8 meter long guitar string, it produces an E note. An E note is 165 hertz in frequency. So this is the fundamental frequency of a guitar string 0.88 meters long. it produces an E note. When you shorten the length of the guitar string by pressing on it, it generates an F note, which is a higher frequency, 175 hertz. So actually, that's how you make music, and that's how you make harmonics in a guitar. You just do it by changing the length of the guitar, and you do it by pressing on the string on the guitar to lengthen or shorten the length of the string. That's actually how a guitar works. So assuming the tension and the speed of the wave in the string doesn't change when it is shortened, what is the length of the string when it generates the F note? And what is the tension in the string if it has a linear mass density of 0.004 kilograms per meter? So we are asked what is the length of the string when it generates the F note. We know that the length of the string is 0.8 meter when it generates the E note. Okay, so how do we solve that? So this is the equation for the fundamental frequency for the E note. It's B over 2L, where this is for the E note. Frequency of the E note, length of the string when it produces an E note. And this is the harmonic fundamental frequency for the F note, F1F. It's B over 2L, where now L is now, this is now the length of the string when it generates the F note. So there are two unknowns here, the length of the F note and V, the speed of sound. The speed of the waves, transverse waves on the string. So we have two equations, we have two unknowns, we eliminate. So there are many ways to solve two equations of unknowns. Here I will use elimination. I will eliminate V by solving the equations for V and then equating and solving this remaining equation here. Solve for the length of the string when it generates the F note, LF. And from here we see that LF is just the frequency of the E note over the frequency of the F note times the length of the string when it generates the E note, LE. So substituting all the values, we get the length of the string when we shorten it to generate the F note to be 0.75 meters. So that's the answer to the first question. So the second question now is, what is the tension in the string if it has a linear mass density of 0.004 kilograms per meter? So we can do this two ways. We can use the fundamental frequency equation for the E note or for the F note. But I suggest you use the fundamental frequency for the E note because all of the values here is given. So we change V by, the V here, we change V by square root of F over mu. So mu is given, the linear mass density is given, the length of the string when it generates the E note is given, 0.8 meters. The frequency of the E note is given, 165 hertz. So the only unknown here is F. So solve for F. And F is just 4F1 squared L squared times mu. So substitute all the given values, and you will get the force of the tension in the string to be equal to 278 newtons. So this is the tension in the string. So we assume that the tension doesn't change when you shorten the length of the string by pressing on the string to generate other notes here. And that is it for the lesson on standing waves and resonance. So I will see you again in the next lesson of chapter 8, which is still on oscillations and waves. So bye for now.